Hello, I'm John Manero from Accu-Slice. This video will be part 3 of the video series on the continuing development of the Automated Accu-Slice System. I had to start over from the original design, which was described in parts 1 and 2 of this video. After making initial prototypes described in these previous videos, I determined the front plate was too small due to the use of a larger and wider linear ball screw and also the repositioning of the Accu-Slice index rail 3/4 inch in from the front edge of the index table. These new designs now use a front plate for the tables that is 10 inches wide. I also changed the design to use 2 linear bearings for the front plate and 1 linear bearing for the rear plate. Therefore, both of the top plates for this automated Accu-Slice system needed to be redesigned and machined. This video describes the machining of the parts to produce these 2 new designs. I will be producing 2 new versions or models of the automated Accu-Slice system. One model will be for the standard bandsaw with a 3/4 inch miter bar slot, and the second design will be for the Hammer Felder bandsaw with a 15mm wide miter bar slot. I once again used my Precision Matthews mill that I converted to CNC in order to machine the various components for this automated Accu-Slice system. I exceeded the size limitations on a cabinet for the mill, and as a result I had to cut 2 holes, one in each side of the cabinet, in order for the 4-foot long metal plates to extend through both ends in order to machine the holes for the various components. The first step is drilling the holes for the linear bearings, and I'm using 2 linear bearings at each end of this main plate. I'm using a long bearing and a short bearing, and I can use a short bearing addition when I'm working with a 3.5 inch distance between the miter bar and the bandsaw blade, but this can be removed if you need a longer distance. The next step is drilling the holes, and this is a .201 inch diameter drill, and I'm drilling the holes through the plate completely. All of the mill operations shown here are actually being shown at 10 times the actual speed, again just for viewing purposes. I actually spent a full day drilling the holes in this plate for the linear bearings, the rail, and also the ball screw. The holes being drilled here are .201 inch in diameter to enable the number 5 screws to pass through. The next step is countersinking the holes, and I'm using a 3/8 inch end mill to countersink the holes so that the heads of the screws will be flush with the top of the plate. In order to drill, mill, and tap any of the holes in this plate, each machining operation was programmed on a CNC mill to generate the G-code. This G-code software then controls the automated drilling, countersinking, and tapping of the holes. In the same manner, the same holes are drilled in the opposite or right-hand side of the plate. Again, 8 holes are drilled, first of all, using a center drill to mark the position for the holes, to make sure they're accurately positioned. And then switching to my .201 inch diameter to drill the holes for the screws to pass through. As I stated earlier, I am putting 2 linear bearings on each end of the plate, and I'm doing this to give additional support for the plate. The first bearing is about 3 inches long, and the second linear bearing is about 1.5 inches long. And it's just enough with these 2 bearings that I can still cut a board up to 3 inches thick using my bandsaw, as long as that distance between the bandsaw blade and the miter bar slot is less than 3.5 inches. And then I'm countersinking the 8 holes for the screws, and this countersink is .200 inches deep to enable the head of the screw to sit below the top surface of this plate. As I mentioned earlier, these drilling, tapping, and countersinking operations are all shown at 10 times the actual cutting speed, so it actually takes me quite a bit longer to machine all these holes and parts. The next step is drilling the 5 holes for the rail, and this rail is situated such that the edge of the rail is 3/4 inch from the edge of the plate. So I started off center drilling the 5 holes, and then drilling the 3 holes with a .201 inch diameter for the tapped holes, and then drilling 2 holes which are 0.245 inch diameter for the pins, and then I use my tap to tap the 1/4 20 thread per inch holes for the screw mounts for the rail. These holes are tapped in the main plate using a technique called thread milling. Next I turn the main plate upside down, and now I'm drilling 12 holes to mount the large covered ball bearing drive system. And I'm putting 6 holes in each side of the plate. And again, these holes are first of all drilled with a 1/4 inch diameter drill, which enables the number 6 screws to pass through the holes. And then they're countersunk with a 1/2 inch diameter end mill. And they're countersunk to a total depth of 0.25 inches. This enables the heads of the screws to be below the surface of this plate and not interfere with the bandsaw table. After drilling the 6 holes on one side of the plate, I moved the plate over and did an additional 6 holes on the opposite end of the plate. Again, using the same process of drilling the holes and then countersinking them. So what you see here in less than 5 minutes actually took me a full day to machine all 4 plates. Yeah, I mounted the rail and the linear ball screw on the plate, so they're both attached, and it still slides pretty smoothly, but I can feel that additional weight. This ball screw is pretty heavy, so even though it slides smoothly, there is additional weight. In fact, if I did not have the legs on the bandsaw, it may have been an issue. I think we definitely need the legs with this extra weight on the table. But it slides pretty smoothly. The next step is to drill the holes for these electromagnets, and I have to make mounts for them too. And then I have to make an adapter plate to go from the plate on the linear ball screw to my sled. So I need to design that plate also. So that's probably the next step, designing this plate and designing the mounts for the electromagnets. Then the next step is making mounts to install the 2 indexer linear stepper motors, one on each end of the plates. I also installed the rail and the linear ball screw on the second system. This is a longer ball screw. And again, it slides pretty smoothly. Next I had to design and machine the 2 1/4 inch thick Delrin plates for the system. A series of holes are drilled into these plates to enable the joining of the linear ball screw to the Accu-Sled 2 carriage. And this is the resulting plate mounted on the system, where the 6 holes are used to mount the plate to the linear ball screws, and then 2 holes with spacers are used to attach this plate to the Accu-Sled 2 carriage. This next step was designing and machining the bar which will hold the electromagnets. In this process, I'm designing and building the system all at the same time. And in this case, I ended up redesigning this later on in the video to make a different design to not only mount the electromagnets, but also to cover them. But again, this was just a series of holes drilled to mount the electromagnets to the plate on the Accu-Slice system. I removed all the components from the main plate on the Automated Accu-Slice system and took it back to the mill to drill some additional holes. And the holes I'm drilling now are for the electromagnet. And the holes in this plate match up with the spacing of the holes that I just finished drilling in the previous bar for mounting electromagnets. And again, these holes were drilled and then later tapped with a 1/4 20 thread per inch tap. I'll be mounting 2 electromagnets to this plate. And these magnets are bar magnets. They're about 4 inches long, about 1 inch wide, and each has a capacity of holding about 200 pounds, so they're pretty strong. So I need to cut 2 slots in the plate to mount these magnets, and these slots go completely through the plate. And this shows the cutting of the first hole. And I did speed this part of the video up 20 times the actual cutting speed, just because it takes so long to cut these slots. And here I'm showing a close-up of the cutting so you can see more clearly what I'm cutting to make these holes in the plate. Yeah, I'm using a 1/4 inch round mill because I need tight corners on the outside edges. And I also need to cut down to multiple steps because of the thickness of the metal. So it took several steps to cut the entire way through the plate. And this is the final step where it cleans the hole up to round out the edges and get rid of any burrs on the holes. In addition, I needed to machine the smaller or back plate for the Automated Accu-Slice System. This plate also has these holes drilled for the linear ball screws, a guide bar locking system, and also holes to mount the two linear indexing systems. The series of holes on the right side of this plate also need to be countersunk to enable the screws that hold the linear ball screws to be attached. And the holes I'm drilling here are for mounting the two linear indexing systems, and these holes need to be both drilled and countersunk so that the screws for the mounting sit below the surface of the table. And I am using two indexing systems to enable the accurate positioning of the index table, and as a result the holes need to be drilled and countersunk on both sides of this front smaller plate. And I'm not showing the drilling and countersinking of all these holes. It's just repetitive what was done in the previous plate. So here's the two finished front and back plates for the Automated Accu-Slice System. So what I showed here in a few minutes, actually I spent a full day making these plates for the two systems. All the holes and slots in this plate have been precision machined for the accurate alignment of all the components on the system. Next I needed to machine two adapter plates. These fit between the indexer assembly and the front plate to accurately position the indexer. Seen here are the 8 holes we drilled in the front plate, and then the spacer plate we made with that same pattern of holes, and this will enable the indexer to be attached to the front plate. This is the assembled system with all the parts that have been machined and completed to date. I installed the two indexers with stepper motors on the left and right side of the plate. Also installed the stepper motor on the linear ball screw. And we also have the electromagnets installed with the bar holding them in place, and also the plate between the ball screw and the carriage to enable the carriage to move back and forth with the linear ball screw. And this completes the system as of this date. Some additional parts were machined for the system, including a new mounting system for the electromagnet and a mount for the Hall sensor. This concludes this video on the machining of the various components to assemble this new version of the Automated Accu-Slice System. In this video I did not show all the parts that we machined for this system. Some of the parts, such as this front bar, the guide bar supports, were described in previous videos, such as the videos on the heavy-duty Accu-Slice system, and also parts 1 and 2 of this video series. In the next part of this video series, I'll be describing the installation of this system onto my Hammer Model N4400 bandsaw. I will also be describing some of the key features of the system that we designed in this system to improve its performance. This new Automated Accu-Slice system is still a work in progress. As a result, some of the parts and components may be redesigned and remachined as I go forward with this project. Subsequent videos in this series will describe the development of the electronics console and also the development of software to make the system fully automated. Once again, thank you for watching this video. If you have any questions or concerns or comments, as always, please give us a call or drop us an email. We're always looking for your feedback to make our systems more efficient and improve their performance. Thank you.